Hello, everyone. Today is, again, we meet on our grad workshop Wednesday meeting. Today we will be talking about human-robot interactions, and we have three speakers from UK and from Colorado University and from Yıldız Technical University. The title is Human-Robot Interaction, and it is defined, HIR is the science of studying people's behavior and attitudes towards robots in relationship to the physical, technological, and interactive features of robots, with the goal to develop robots to facilitate the emergence of human-robot interactions that are the same time efficient, but are also acceptable to people and meet the social and emotional needs of their individual users, as well as respecting human values. That is the definition from Dutenhan, 2013, from that paper. And robots are in every field of our lives, and the terminology is also a little switching from the human-computer interaction or the term human-robot interaction, slowly substitute the term social robotics. Today we will be talking about some of the studies done in this field. Our first speaker will be Hooman Hedayati from University of Colorado. He completed his PhD with the Dr. Daniel Zafir from the computer science department. And after that, we will be Merve will be talking us about social navigation in robotics from Yıldız Technical University, working with the Sırma Yavuz, Professor Dr. Sırma Yavuz. And our last presenter will be Istanbul Technical University. It's a thesis conducted in Istanbul Technical University, Hasan Kıvrak'a. At the present time, he is in Manchester University in UK. So now I guess I will stop sharing my screen so that then here. Okay, our first speaker will be Hooman Hedayati. Hooman, if yes.
Sure.
Yes, everything is fine. We are with you, Hooman.
Okay, thank you so much. Hello, everyone, and good afternoon. Thank you so much for having me here. My name is Hooman Hedayati, and today I'm going to talk about my journey over past 8 years. And most of my work was funded by NASA, and I had a chance to work at Microsoft Research and Disney Research. A little bit about myself. I finished my PhD at the University of Colorado Boulder. Then I moved to University of North Carolina, Chapel Hill for doing a postdoc. And my next destination, it is going to be a postdoc at Kyoto University. And since the borders are closed, I had a chance to stop at beautiful Istanbul. And I am on my remote work / vacation mode. So my vision of the future is robots are going to be everywhere. They are going to be in our conversational groups. They are going to help us learning new skills. They help us with groceries. They are going to show us directions, and they are going to be our companions. But where are these robots? If you look at the state-of-the-art robots now, you can see that we are far ahead from my vision. So as you see a robot in this combat, and as you see the interaction with the soldier, it is not as it is expected. Or if you look at this lady working with Sophia, you see that weird laughter of her. So right now, we are not ready to accept the robots in our life. One of the problems that avoid us to reach my vision is that we have something named perception mismatch. The user, the human, see the world in one state, and the robot see the same world, the same environment in whole another different state. And there is a mismatch between these two perceptions. So over past 8 years, I was working to bridge these gaps. We need to make the robot that can communicate the information better to the human. And also we need to design robots which can understand human behavior better. For the first direction, my goal was to design better robots. And I published a couple of these projects in HRI, IDC, IROS, and CHI. So the first idea is that to bridge the perception mismatch gap is how we can utilize augmented reality to show the goal and communicate the goal of the robot to the user. So you can see a video of a user wearing a head mount display for augmented reality. And as the robot moves, the robot can show the direction that the robot is going to the user. Or in this situation, you can see the video feed of the robot on top of the robot. And then with that technologies, we can communicate more information to the human. Or the other project that have been done in the same setup is that for a teleoperator, it is hard to control the robot. Sometimes if we are in the cluttered space or a dangerous place that we don't have the chance to risk the robot or the environment, then we can use augmented reality to help us navigate the robot better. And moreover, I try to convey the information to the user that no one really looked at. So we were thinking that if we want to have a better interaction with a human, we need to go closer and show affection to the user. So we study how people hug each other, and then we create a soft manipulator that can mimic exact same pressure to the user. And then finally, we put that manipulator into the giant panda. And in the user study, we find out that children, especially children, really love this type of robots and this type of interaction. The other project that I've done in the same setup is that how the robot can show emotion to the user. So for example, if a user go close to the robot, how robot can communicate that don't come close to me, I am dangerous. So we used expandable structure for this purpose. So we create a Hoverman sphere on top of an aerial robot. And the idea was that whenever user go close to the robot communicate that don't come close to me, I am dangerous. And this is one of our 6 design that we have. Or one last project in this direction is that how we can convey awareness to the user. And for example, if a user is wearing a virtual reality glass, and then he or she sees a chair in the environment, how we can protect the user, and then once the user wants to interact with that chair. So how we can convey this information to the user? So we create a robot that can deliver a furniture for the user. Same as the Pufferbot, the project that I show you, we have another expandable structure on top of a robot, which can bring furniture to the user. So in that case, when the user is wearing virtual reality, we can move walls, we can move chairs and furniture, and try to mimic the same environment to the user. Or the user can interact. For example, if it brings a chair and wants to sit on it, the robot goes and brings a chair on the same spot, so the user can have more immersive experiment. All this project that I showed you was in the direction of making robots which can convey more information to the user. But I have, for my dissertation especially, I work on the other direction, which is how we can make robots to understand and then predict humans' behavior. And for this section of the work, I'm more focusing on human-robot conversational groups. So this is a hard problem to solve. For example, if a user goes close toward the robot, how the robot should know that this user wants to start a communication with the robot, or it is just passing by. And we are still don't have absolute answer for this scenario, but my focus was more into freestanding multi-party conversational groups. And all of the contribution that I'm going to show you in a second is not just by reading the literature review, but it is more by my experiments at Disney Research and Microsoft Research. So this is a direction robot that we have at Microsoft Research.
Can I help you find something?
Yes.
The purpose of this robot is to show direction to the user.
Conference room 3800.
To get to conference room 3800, go to the end of this hallway. Turn right and go straight down the hallway for a bit. Conference room 3800 will be the first room on your right.
Thank you.
So as you see, this robot is performing a really complicated task as gesture, as natural language processing. But for the basic stuff, we need to know that who is talking to this to the robot and who is not. Or at Disney Research, I had a chance to work with Character Robot, which is a humanoid robot with capability of having interaction with the users. So my contribution for this field, human conversational group with robots, is that I create data sets that people can use. I try to compare human conversational group and human robot conversational group. And then I propose a method to detect conversational groups. And then I characterize different formations. And I detect missing people in the conversational group, and lastly, identify the group attention. Since it's going to be a short talk, I'm not going through all of this contribution, but I thought that it is beneficially if you know that the data set existed and my last two work. So I'm going to only show two projects out of those. And then the word affirmation that I'm going to use a lot in this talk is already hardwired in your brain. So if I show you this picture and ask you who is talking to whom, or detect the conversational group, you can easily detect the formations here. So we have an formation of a size 8 here. We have a formation of size 4. We have a formation of size 3 and size 2 there, and that is all. So I'm going to skip the definition of the formation, but whenever I said a formation, you just consider it as conversational group. And these conversational groups or formations can appear in different ways. So it can be circular, it can be L arrangement, vis-a-vis arrangement, and a side-by-side arrangement. And for gaining information from all of them, we need a data set. So I created 3 data sets. One is just a mean data set at Disney Research, and in this data set, we have the formation or conversational group of all the people in that conversational group are human, and also a formation of a formation with a robot in it. And then this is the number of the frame that we have. And then I had another human conversational group, and the name is Babel, and this is consisted of 60 minutes of people talking to each other in a conversational group, and they are wearing a motion capture, so we precisely know what are their position and location are, and this is like publicly available for your use. And then the last one was the information from the direction robot, the robot that I show at Microsoft Research, and the data here is gathered from the Kinect and RGB camera on the robot. So just wanted to know that this human robot datasets are available if you want to use them. I'm going to jump to my 5th contribution, and the reason that I'm describing them to you is because they are like the most recent research that I've done. So one of the problems with detecting conversational group is that sometimes because of the sensor or because of noisy data or a formation detection algorithm, one or more users are missing. In those cases, for example, here, the robot sees only 4 people and then ignoring a user in that conversational group. And then that is really hurtful for human-robot interaction. So the idea of this project is that even though if we don't see a user, can we still predict their position in the space? So as you see here, 3 people are having a conversation, and all of them wearing a hat, which the robot can detect them.
We stalked anyone recently?
And
no, I noticed that Kara.
A 4th person come, and she's not wearing a hat, so the robot cannot detect her. But because of the algorithm that I created, the robot can still reason about her. And the idea of how this magic works is that we compared all the information of the same size with each other. So we we pick one of the information of size, for example, 3 here, and we transform all those information to the position 0, 0 with orientation of 0. And then we repeat this transformation for all the formation. For example, if we have another formation, as you see on the right, we transform it and laid it over on the previous formation. If we do it for all the formations, then we can have a heat map of where people are going to stay. And as you see, people tend to stay on the same location respect to the robot. So we used this to train a classifier, and basically we teach the robot that if people are like all the formation of size 4, people tend to stay on this formation. And then when another person join to the conversation, the two people, the two highlighted people on the right, they are going to move a little bit and change the position. So the robot can reason that, okay, now with this position of the people, although I cannot detect the 5th person, but I know that the formation is of a size 5. And then we kind of tested over different data set, and then we find out that this is a reliable reliable result. I'm going to show one more a video here, and as you see, a newcomer comes, and then again, because the two people are shifted, we kind of predict that there should be a formation of size 5. So the takeaway here is that with the noisy data or with the sensor, with the noisy sensor, we still can predict the position of the people in a conversational group. So I'm not sure, but how am I doing on time? Can I still have like 4 minutes to show another project?
Please. Yes.
Okay, cool.
5 minutes. Cool.
Sure. Yeah. And then the 6th contribution, and this is going to be a little bit of I'm not going through the math, but I'm going to show this project too. So the idea is that how robot knows that where it should look in the conversational group. So the robot that you see here does not have any microphone array, or it doesn't have RGB camera. So it does not it doesn't know anything about what's happening in this conversational group.
So probably don't want to hear that. Another one that got ruined for me was McDonald's fries. They are not vegetarian.
So as you see, the moment that a speaker switched, the robot predict who is talking, who is the person that is talking, and look at that person. So the idea here is that current state of the art is either using RGB cameras. For example, if this person is talking, because of the people use face detection or lip detection algorithms, and then find out who is talking, and then use like visual cues. Or the other methods that people used is one disadvantage of using visual cues is that, for example, in the pandemic time, people are covering their face with mask. So the lip detection or face detection is not as robust as we wanted. Or the other solution for that is people use microphone arrays. So with a microphone array, you can find out where the sound is coming from, and then ask robot to look at that direction. The downside of using this approach is that if there is another person who is louder, or we are in the noisy place, then it confuses the robot. So to solve this challenge, we come up with the idea of we can rely on the position and orientation of other people. So for example, as you see here, the two people are looking at the third person, and then because the two people are looking at the speaker, then the robot can reason about where to look at.
Yeah, I've heard some about
My whole
that.
lifetime. Yeah, so
And then the moment
I've been to several national parks already.
the active speaker change,
Zion National Park
then
is nice
the attention of the group change, and then the robot understand that.
Mount Rainier.
Oh yeah.
And of course, Rocky Mountain.
And right.
Sand dunes. Yes.
And then one advantage of using this algorithm over past approaches is that most of time the point of attention point of the group is not the active speaker, but it can be anything else. So for example, in this setup, I'm bringing a poster without telling to the participants. So because someone new comes to the conversational group, then all the people are looking at that poster or that distraction, and then the robot acts the same. And when the people lost their interest in the new object and continue their conversations, the robot behave the same. And this was interesting for me, but this solution works with two people.
Oh, you could have like a new bench every like month. New bench every month. You could only really sit on it for like the last
So
week.
I've actually been thinking about that a lot. I just read a few papers where they had a ton of like foam prototyping. I forget the name, but you know how people take blocks of foam.
Yeah. So with that said, the takeaway from this project is that we can use hidden Markov models for detecting the group points. So these are today. I try to give a short summary of my work over past 8 years, and I hope you enjoy it. And I hope that with these algorithms, we can achieve to my goal, which is a better human-robot interaction. Thank you so much thank you to all my collaborators, and thank you so much for listening to my talk. And if you have any question, please email me at Hooman Hedayati'ye@colorado.edu, and I'm happy to take questions.
Thank you, Herman. Very informative. On my behalf, I learned a lot, an interesting speech. If you have any questions and comments about the presentation, we can have it now. I want to ask something about the missing people detection solution. So your approach is first shift of group of the people, right? It's the data for the robot to detect that. And also a little bit advanced thing is group attention, right?
Yeah, sorry. Okay, sorry, can you repeat it one more time?
So about the solution for the missing people detection. So your first approach is the shift of the people when the newcomer joins the group, they change their position. So that's a data for the robot to understand that there's this newcomer, right?
Yeah,
and
that is right.
A little bit advanced level is the group attention. When they turn their faces, right? So the robot detects that there's this newcomer and talking kind of thing.
So that is right. The first there were although it looked like similar, there was a little bit of different projects, but on the same environment. The goal of the first one was that how we can use the information that we have from information data set, and how to use them to detect missing people. So that was a data-driven approach for just detecting the missing people. But more that the second project that I skimmed through was more into this idea of, okay, now we can like detect a conversational group. Now we can know that if we are missing a person or not. But to make the robot more intelligent, where the robot should look at, and then trying to use machine learning algorithms to detect the active speaker.
I'm out of curiosity also, did you try to act like, I mean, like try to make the robot as full, because the group may act like there is some newcomer, they can change their position, and we can talk to
oh yeah,
no one, there's nobody, so the robot will think that there is something, right?
Yeah. Because of if that happens, definitely the robot can
the robot, you know.
Yeah, that is yeah, we've not that, but that is exactly we can like fool the robot with that.
Okay, there is a question from Hasan.
Yeah, I just wondering what can be the application areas of your research. For example, how can the robot use this information gathered from the classifier or another techniques you have used? How can it behave accordingly based on this information?
Yeah, that's a great question. I believe one of the application of these work is that so when I was at Microsoft and then with that robot, we find out that the robot always confuses people who are passing by, and then when two people were or three people were talking, but with the robot only addressed only two of them, not three of them. And then the idea was that sometimes we had a problem that the robot didn't look at the active speaker. For example, the robot, like someone is talking in the group, but the robot is staring at another person in that conversational group. So all these algorithms that I presented for the conversational group can be implemented wherever we have a conversational group and a robot that is like there, and I think that in general this can like improve the experience of the user. And one the other application that it is going to be I'm thinking of, I think Merve was the person who was working on social navigation, but with the formation, with knowing the conversational groups and detecting them correctly, we can use this to help the robot to kind of respect social norms, because when people are having a conversation, you don't want to cut through of them. You want to always respect them and like kind of like go around them. So these are like a couple of applications that comes to my mind.
Exactly. I'm also working on the social navigational task.
So maybe it was
and also
you. I was just like,
for also if the robot wants to start a conversation, the approaching was maybe an important point. So if the robot knows the position of the other people, for example, it can approach accordingly with a social being, for example. Yeah. Thank you very much for your answer.
Yeah, thank you so much for the question. I'm excited to look at
because
your talk.
your is also very related to our work. That's why I'm interested. Yeah, thank you.
Yeah.
Human also, the way your experimental setup reminds me of the human nature. Like the robot is not recognizing the newcomer if she is not wearing the hat you define, right? So it is just like, I could ignore some people in the group because they don't wear the hat that I want, right? So, you know what I mean?
Yeah, that.
So it's kind of, you know, well, if you want to be noticed in the group, you have to play the with the rules of the group, right?
Yeah, that is right. Or
that's human nature. Okay, thank you for the presentation.
Thank you so much.
Okay, our next speaker will be Merve from Yıldız Technical University, studying with Sırma Yavuz Hocam. Okay, Merve, we are with you. Can you? Okay.
Yes, can you see my screen?
Yes, everything is fine.
Okay, wonderful.
Good to go.
Okay. First of all, ladies and gentlemen, welcome to my presentation. I would like to thank the Graduate School of Science and Engineering for this invitation. It's an honor to be here. And first of all, let me introduce myself. My name is Merve. I'm working as a research assistant at Bahçeşehir University Department of Software Engineering. And I'm also doing my PhD in computer engineering at Yıldız Technical University. Today, I'm going to make a mini presentation on my doctoral thesis, which is about social navigation in robotics. And let's start with the outline. This is the outline of my presentation. First of all, I will start with the motivation that led to this work. Then I will summarize the work done on this subject and describe the solution and method that I will use in my own work. And finally, I will show my references, accept your questions, and listen to your suggestions. And now let's start with the motivation. Since the beginning of history, mankind has been after inventions that make life easier. The history of world technology has come a long way with the digitalization following the industrial revolutions that started with the invention of the wheel and continued with water and steam power. With the development of digitalization, it has come to the present day by including information technologies, the introduction of cyber physical systems, and finally human-robot interaction. Robots are the most popular of these technological phases and the subject of many news and discussions today. Human-robot interaction is a research topic that focuses on how robotic systems used by humans in the same environment should have a design for safe and efficient work. In this context, robots try to understand humans by seeing, hearing, and feeling like humans. For this, robots use artificial intelligence algorithms based on image processing, voice recognition, and contact sensors. With today's technology, more humane robots and robot movements are needed due to the widespread use of robots and their inclusion in social life. In this context, the aim of the study is to develop an autonomous robot that can sense the environment, integrates with humans, is safe, flexible in management, and uses a social navigation. With this study, a domestic service robot that provides fully autonomous navigation will emerge for the first time in our country, and it is aimed to take innovation steps by using deep learning techniques in autonomous realization of social navigation skills in dynamic environment. In the literature, actually, when I started to research this topic, there is no study that can perform social navigation in crowded environments with deep learning methods in solving the problem of navigation in autonomous robots. The robots, which will be developed within the scope of this study, can make important contributions to the international literature by having all these features together. Instead of using ready-made platform, the creation of domestic and open to development robot model and software infrastructure will contribute to new expansion in different application areas. Now, I want to continue with the literature. With the fourth industrial revolution, studies have mostly focused on interactions where there is a physical association. That is, for interaction to occur, the robots and human must be in the same place at the same time. In addition to this, the importance of the nature of this unity is emphasized. For example, the interaction of a robot that always does repetitive tasks in the fixed place and the interaction of robots that do tasks related to the care of mobile aged people will be inherently different. It is useful to explain the terms that are frequently used in human-robot interaction studies and often lead to ambiguity. The team of researchers from the Technical University of Munich states that human-robot interaction is an umbrella term and encompasses human-robot coexistence, cooperation, and collaboration, and lists their differences. In figure 1, you can see these items, these terms. Now, I want to explain them a little bit. Coexistence means human and robot working in the same workspace at the same time. Cooperation means human and robot working at the same time in the same workspace and for the same purpose. For the last one is the collaboration, human and robot working at the same time in the same workspace with physical contact for the same purpose. So this is all about the terms. I want to continue with the techniques right now. For the human and the robot to work together safely, the robot, it needs to perceive human inputs. To understand and predict human intention, the multi-modal technique, which is mostly 3 techniques and combination of these techniques is used. Actually, the techniques are listed here. They are gesture recognition, speech recognition, and physical contact recognition. Gesture recognition is a communication method between the human and the robot, and the human facial expressions, hand-arm movements, or the posture of the body can be made detectable by image-based techniques or wearable devices like sensors. Detecting these messages, the robot can perform message-specific tasks. For example, when it detects a person with a raised right hand, he can immediately stop all his movements. And gesture recognition technique is divided into 2 categories as image-based and non-image-based methods. Today, of course, I will not talk about them. And the second method is speech recognition. This is another technique. It is divided into speech recognition, language recognition, and recognition of environmental sounds. Sounds such as the sounds of surrounding devices and thunder can be given as examples of environmental sounds, unlike the human voice. Studies on natural language processing and human-robot interaction systems have intensified and progressed. And today, just like on our mobile phones using speech-to-text applications, we can convert our voices into text and thus into messages that can be understood by robots with very high accuracy. And the last one is the physical contact recognition. Involuntary human-robot contact often requires sudden robot stops. Sudden robot stops can be detected during contact with force torque sensors attached to the robot or just before contact with capacitive sensors. The robot performs the planned output according to the input, of course. When the robots hit an object, the impact can be felt as there will be some unexpected changes in power consumption and planned action is performed. Actually, at the beginning of this technique, I said that we will use multi-modal technique. This is a technique in which voice recognition and motion identification systems are used together to obtain more efficient and safe outputs. Now, let me show you another example. So far, we mentioned the general concepts or terms about the topic. And here I want to give you some real-life example. In this study, human-robot interaction strategies are presented for the avocado harvesting process based on non-verbal communication methods that provide movement directions to a robot during the social navigation. It has been shown that it is possible to construct a human-robot interaction architecture based on original harvesting process derived from the visualizations. The possibility of humans sharing the workspace with robots has provided farmers with new opportunities to increase process efficiency and reduce human workload, and is presented as an area that should also be evaluated in future studies. The presented human-robot interaction schemes are aimed at improving agricultural process that cannot be fully automated due to their complexity. In figure 2 on the left side, you can see different circular zones that fit into a person's personal space. When a robot navigates sharing its workspace with a human, it must respect social zones to improve its social acceptance. Therefore, when a robot approaches a human, the distance between human and the robot must be within the social space. You can see on the right side, there is another figure in figure 2. It shows several possible areas where the robot can approach or follow the human, and calling these areas socially acceptable areas. In figure 3, there is a flow chart that is summarizing the process. It has been observed that the farmer can harvest from the ground or using a ladder, and then interacts with the robot and deposits to the collected crop on it. The robot's job is to transport the crop boxes to the cargo truck area where a human picks them up, perform a visual inspection, and drop them on the cargo vehicle. The robot always navigates the field using social accepted criteria until a human needs a help. The human-robot interaction architecture in the study aims to help reduce human workload and increase the efficiency of process by increasing the volume of crops harvested daily. And in figure 4, the general principle of the study is illustrated. Now I want to continue with the next study, which is COMET. In this study, a new approach is presented for calculating the cohesion of a group and using it to improve the navigation of a robot crowded schemes. The approach uses a new fit metric that builds on previous work in social psychology. This metric was calculated using various visual features of pedestrians from an RGB camera on a robot. Specifically, features corresponding to proximity between people were identified for relative walking speeds, group size, and interaction between group members. The cohesion metric was used to design and develop a navigation scheme that takes into account different group cohesion levels as a robot moves through a crowd. In figure 5, the use of COMET metric to calculate a collision-free trajectory for a robot in real-world scenarios is shown. COMET identifies groups in crowds and detects within group proximity, walking speed, group size, and interaction to predict a group's cohesion. On the left side in figure 5, we can see a dense scenario. The navigation algorithm identifies a low cohesive group and navigates among group members, assuming human cooperation for navigation. On the right side, it detects a higher harmony group and plans a trajectory around it. In figure 6, it shows how the approach is used on 2 different pedestrian groups at a given time. Group 1 consists of 2 pedestrians moving away from each other, close to each other. In the next frames, their distance increases and they look in different directions. This means very little interaction and low group cohesion. And group 2 consists of 2 people walking facing each other, showing high interaction and high group cohesion. And in figure 7, you can see the architecture of socially compatible navigation algorithm, which is used in this study. Now, let me talk about the solution. First of all, I want to talk about the planned goals. As you can see, we have 3 main goals. In addition to solving the problem of autonomous navigation in 3D dynamic environments, we will develop a service robot capable of social navigation in crowded environments with deep learning methods. And adaptive dimensional 3D local cost maps are very important, and they are not available in the navigation methods in the literature. At the same time, there is no package that provides a 3D cost map implemented on a robot operating system platform that is planned to be run on the service robot. With this study, a navigation algorithm that can effectively generate and use 3D cost maps that can adaptively change in size will be produced as a unique value. Now, I want to explain the social approach part. During autonomous navigation, it is aimed to create the possible movements patterns of the people around them, to understand their possible future behaviors, movement trajectories, and to adapt their movements in a social way according to the human beings. This is very important for the formation of trust in mobile service robots working with humans. Since people will take a stand according to the movement of the robot must adapt his movements according to the human. For example, people may be uncomfortable with fast-moving objects in their environment or being close to them. For this reason, the robot should make its movements at a speed and distance that will not be perceived as dangerous by people in environments where there are people. It should be able to make decisions such as whether to give way to people or to reduce their speed in places where there is a higher probability of encountering people, such as the junction of 2 corridors, the entrance or exit to the room. And at this stage, the service robot must first detect the type of obstacle and exhibit different behaviors for human and non-human objects. Although convolutional neural network gives more successful results than classical methods, especially in computer vision applications, a large amount of data is required to train the complex network using the GPU. Also, the robot uptime may be shortened in real-time applications as the GPU consumes a significant amount of power. In order to reduce such problems, it is planned to make use of the instant 3D maps of robot alternative. And this is the method. I share the main items of my roadmap with you. First of all, the system architecture needs to be created. Then before starting the real life tests directly, various environments in the simulation environment must be designed, and the robot and the designed environments must be analyzed. As the final stage, real life tests are planned to make improvements actually. So where are we at? We have completed the first stage. Our experiments continue in the second stage. After completing this stage, we will perform the last stage with real-world tests. As I just mentioned, our experiments are currently ongoing in the simulation environment. Therefore, it wouldn't be correct to share the results without completing the experiments. I hope we will discuss both the simulation results and the results of real-life experiments in another workshop in the future. So these are my references for this presentation. Thank you for listening. If you have any questions or suggestions, I will be very happy if you share them with me.
Thank you very much, Merve. Thank you, Sırma Hocam. If we have any questions and comments, we can have it now. Bakıyorum. For myself, I would like to ask you talk about the recognition methods, right? Gesture recognition and speech recognition. Merve. I just want to ask if they have the same weighted average. Like, do they also? I'm not sure if you did this test, but do they also check the consistency between the gesture and the speech? Like, I could put a happy face, but I can use very angry words. You know, I can send you mixed signals.
Yes, you're right. I'm not working at that point. My friend will work that point actually, but you're right. Sometimes the people or human are happy, but they are not showing them very well. So they are mixing, they are fixing the robots. Actually, in the facial recognition part or the gesture recognition part, I know that there are some action units, and that with using them, they can decide the feelings of the people. So I'm not working that topic, but I know that this part.
For also like the communication, like human being as well, we say the facial recognition is, I mean, giving the real information. I mean, I do not trust your words, but the mimics are more credible, I guess. This is the human nature. So I don't know if they have the same weighted average as the data. Like, yes, gesture is more credible, maybe. I don't know.
Yes.
Okay, thank you very much. Is
No
there
problem.
a question? Do I miss anything? I guess everything is very straightforward and clearly presented by Merve, so we have no questions. Thank you, Merve.
No problem.
Human-machine interaction, human-computer interaction. And which one is a broader umbrella? Or
human-computer interaction. Yeah, so human-computer interaction, I think I can share my screen.
Well, they also have human-machine interaction, human-robot interactions.
So,
because I wanted to put the name to the workshop to human-machine interaction, but I don't want to make a mistake because I'm not from the field. You could say that, oh, that's a totally different area. So I understand.
Yeah, so I'm going to show a video. Maybe it is going to be helpful. Give me a second, please. Yeah, let me find it.
Or the,
okay. Yeah, so
can you share your screen? Is there anything?
Yeah.
We may also have some questions and comments from the attendees as well.
Yeah, I think so. I don't know. It was 70s or 80s that the human-computer interaction the conference started. I'm going to share my screen really quick, and then so sharing my screen. So if you see at the CHI conference or human-computer interaction, it is more into like all the things that you can do with your computer, tablet, or cell phone. And it can be anything. Like this is like just all the paper that presented. It is like information retrieval is a thing, like gaze, or like how you can use gaze for better programming is the thing. The textile and like using it as an input to the computer is a part of human computer interaction. So this is like a broader umbrella that can and then this is like augmented reality, virtual reality. So I'm going to say that human computer interaction, or CHI, it is the umbrella. It is going to have all the things that like how you deal with your computers. It can be using like different inputs to the system, output to the system, virtual reality, augmented reality, or privacy is under a CHI. So it is like a giant conference. And then this is like the I think it is biggest conference into the field of like except for machine learning, CVPR and like all those conferences are like bigger, but CHI, it is more focusing on how people interact with their computer. And then the computer can be tablet, it can be like cell phone, it can be like anything. It can be as a computer. But then there are like smaller sub-conferences that have a different name. So for example, if you are more into the robotics and you want to do something autonomous, it can be like HRI, which is my field. If you are more using computers as input or output devices, then the conference is VIST, or if you are going to do like augmented reality, virtual reality, IEEE VR is the conference. So I think almost like all the like field of computer can be seen as a human computer interaction. And then like human machine interaction is the same as human computer interaction, but human robot interaction is a subfield of it.
Thank you. And the videos are really mind-blowing. I like thank you very much.
So I think that I'm going to send the video in the chat, but each year, since CHI is a giant conference, each year they have like a teaser of like all the research that's submitted to that conference, and then it is like 2-3 minutes, and it just showing glimpse of like what the trends are, and it is like nice to see. So I'm going to share it here if you want.
Thank you.
You can see like previous years too.
Hasan is also back to. We have 2 Hassans, which is real. Which one is real? I don't know. So maybe you can share, Hasan, your screen as well. Okay. And from the chat box, you can get the video link from Hooman. Thank you, Hooman, for the comments. Hasan, we are with you.
Okay, thank you very much. I'm very sorry for unexpected situation I have faced. Okay, first I was to start with the mobile robot navigation. And as we stated from the previous presentations, we see that robots are becoming our part of life. Maybe at warehouses, at the malls, at the offices, hotels, hospitals, the hotels, restaurants, and airports. So the robots that have been operated in such a human environments needs a unified navigation approaches, which they expect to interact with the humans explicitly or implicitly, verbally or non-verbally, based on the context we are aiming at. So our robots needs more social intelligence and more social skills when they want to improve a better human-robot interaction. So just I want to mention that the robots are very close to humans, and nowadays, and it's going that this interaction will be much more complex at the near future. So the study, my study is a part of a Turkish Scientific and Technological Research Council project. That project was actually aims to develop an assistive hospital robot for children, and my study was specifically focused on the navigation of assistive mobile robots. And to do so, I wanted to develop a social navigation framework that will generate a human-friendly paths among the people, maybe in a hospital scenario, or we can enlarge it for an airport scenario or a shopping mall scenario, something like that. And there can be different types of humans. There can be elderly peoples, they can be a child, or different types of human can be located in the environment. And the question is, our research question is, can we develop a better navigation algorithms that will be accepted by the humans, and the robots will also accept it as a social being, and they won't feel any annoyed or intimidated by the presence of the robots in the environments. So that's why in the literature we have some traditional navigation algorithms, but these algorithms mainly disregard the presence of intelligent agents. Particularly, we are saying the humans here, because they are acting all the objects that are being being avoided, and they don't detect the type of the obstacle, for example, and they don't behave differently to the human or the other objects. And also they don't take the social constraints into account, such as proxemics. Proxemics are the human spaces, human use spaces. There are maybe the Merve also presented about this one. And there are intimate space, a personal space, a social space, and other spaces. And also comfort. This is the traditional algorithms only satisfy the physical comfort, but the human beings has also psychological comfort. And also the motion of the robot should look like as a nature by the human. And if the algorithm is not social, so they are mostly inoffensive and uncomfortable to the humans, and they are insufficient to produce a socially acceptable behavior in the human environments. So the robots that are deployed in such these environments need a better or an algorithm beyond a simple collision avoidance. And with these algorithms, we are going to ensure the humans not to be annoyed by the robot presence. And this is our ultimate goal. When we put these robots inside the humans, humans cannot be annoyed, and it will be accepted as a social being, like a human. This is the ultimate idea of the most social navigation algorithms. And that's here I want to give some literature, the algorithms that exist on the literature. I can differentiate it into two parts. One is the learning-based social navigation. Here, the idea is to learn a function that the experts or the humans use when they make some particle decisions. Because as we are humans, when we are on the human environment, let's say we are in a passing in corridor scenario, and we know how to behave. We have our inner dynamics, our inner function that is learned by the experience So the learning-based algorithms are trying to understand what is this learned, what is this function using the reinforcement learning algorithms via the trial and learn approach. And there is also inverse reinforcement learning is used, which is the learning the reward function. So in which step should I go for the to get more reward in the environment? And convolutional network-based approaches are mostly getting the images and then take decisions accordingly. And there are the hybrid version of deep Q networks with the CNN and reinforcement learning. And the second approaches can be categorized as a model-based social navigation. And typically these approaches uses a modeling, mathematical models or social cons functions into the motion planners. The most common one is the social cost maps. Instead of using just cost maps, we use an adaptive social cost maps based on the human interaction. For example, if the human is moving, so the cost map is populated along the walking direction. And if it's static, for example, it's just a circular shape. And if the person is angry, for example, we can enlarge the area of the social cost map and such and so forth. And there are also algorithms which are adopted for the human environments. These are the very popular rapidly random trees and the dynamic window approach, which are used in the literature. Velocity-based approaches and also social forces. In this talk, I'm going to talk about the social force idea. And this idea is not a very new idea, actually. It is in 1995, it is introduced to predict the human motions in escaping scenarios. Actually, it's based on the prediction, the human motion prediction, and is extended by different researchers. I won't go into details. Here, you know, I said for escaping scenarios, for example, they want to understand the inner motion of humans and how do they behave when they are in an escape scenario, and they are going to design the architecture according to, for example. And then this idea, when the social navigation approaches are becoming popular, then this idea is considered to adapt it as a local planner on robots to behave human-like. If it really replicates the human motion, then can we also use it for robots to behave like a human? And it is used as a different scenarios, walking side by side. For example, in this study, the robot is walking near the human, so they are engaging with a walking scenario. And for the not so dense environments, if there are few people on the environment, so we can use some different collision prediction models to have a proactive motions and so on. And this is also very related to the Hooman study, because we also need to deal with the human groups and human object interaction. For example, if there is a human group, the social behavior or the social decision should not be disturbed the human group, or if the human is interacting with an object, you shouldn't be annoyed by passing just center of the interaction, for example. And the social force model is a very lean theoretical approach. It's basically consists of two parts. One is the attractive forces, and the second one is the repulsive forces. And in this idea, we think that human behavior is affected by some forces for acceleration, deceleration, or directional changes. So we are making decision based on the total force that we are exerted by the humans or the static object. For example, this static object make a repulsive force. It is push away from it, not to close, not to crash this object. And human also was pushing the robot. And these are called the repulsive forces. And the goal is attractive force because it's pull itself. We want to reach the goal. And the total summation or integration of all the forces are is called the total force. And we expect the robot to behave based on this acceleration vector. So basically, it calculates the attractive and repulsive forces and outputs an acceleration vector. Okay, so so based on this acceleration, we can predict the next time, the position of the next time, for example, using the 1/2 t square. Okay, these are the definitions of attractive force. It can be specified differently in the conventional social force model. It is defined as a velocity-based force. So this is the graphical interpretation of this formula, and we assume that the human is going in this direction with a velocity v. And actually, we want him to, or she, her, to desire this in this direction. And it is the attractive force is defined as the subtraction of these two vectors. So actually, the human is going to be pulled in such this way. And the repulsive forces are specified to keep a certain distance from the non-intelligent agents in the environments, the walls, obstacles, or static objects. And it is defined as an exponential decay function with the Euclidean distance vector. So as we look at the formulation, here we see a Gaussian-based formulation, but it just used the Euclidean distance, the distance between the robot and the human and the obstacle is taking into account. And these E and B parameters are the hyperparameters that modulates the strength of the vector and also the interaction range. Okay, so for example, if we are approaching the obstacle, it's exponentially increasing, and when we are moving away, it's exponentially decreasing function. So the vector magnitudes are changing based on this formula. And of course we sum up all the forces on the environment. And this approach is not a proactive approach, it's a reactive approach because it's increasing while you are closer to the object. And for example, for the humans, we can define different type of repulsive forces. In this example, for example, the aim is to apply a force beforehand. If there is a conflict point, for example, we calculate the nearest distance that will happen on the feature. So it is the 90-degree vector here, this position, and we apply the force as if the human is here. So that gives a much more proactive behavior to react beforehand while you are so close to the human, not to violate the social distance of the human. So it is the same. The formulation is just a little changed. So just you add the kesme işareti, I don't remember. You just change use this distance, and you modulate the vector based on the time you are going to conflict and the velocity of the human. So, okay, if we understand the theoretical background, now how we are going to apply for the robot navigation, because robots has some inherent constraints, because not flexible as the humans. Humans can turn around 180 degrees and then can make sudden changes, whereas the robots has not so much flexibility because they are on wheeled platforms, right? So, and we need to feed some linear and angular velocity to drive the robot. So we should calculate the wheel velocities to drive the robot. And another problem is the oscillation problem, because when there is no object on the environment, there can be some incontinuities, and the force can be reduced directly, so it can make some oscillations. So the first option is the constraining the change in forces to impose the continuity. And there is a well-known problem, is this stuck on the local minima, because this is a potential field method, and it can stuck on the local minima. This is the local minima condition. For example, while the goal is attracting the robot, the obstacle is pushing away from it, and these two forces as balance itself, and the robot got stuck, and we call it as a local minima situation. And one solution we have suggested for this problem is to have a global path, to extract a global path and find, since this is a very dynamic and evolving, changing environment, it is not so expected to follow a current path. That's why we have extracted some key path points to follow, and we have solved this issue. Okay, we have our acceleration vector, and we want to calculate the steering and the driving velocities. So we again use a very lean approach for the robot controller. We have calculated the steering angle as the difference between, this is the robot orientation and this is the total force. So there is this kind of, and actually the robot needs to be turned within this degree. So we have calculated that degree to move the robot, to steer the robot to the goal, and as a linear velocity, we use this approach. At high steering, the robot needs less speed. It is like you are approaching a junction, and you are going to have a very strong steering. So you brake the pedals, right? So you reduce your speed. So as the angular velocity is increasing, we are linearly decreasing our linear speed. So we actually calculated our linear speed based on our angular velocity, and it works. But there may be some different also controllers, maybe some much more complicated controllers. And this was our robot we have used in our experiments. It is a two-wheel differential drive robot with sticking with a tablet for the human interface to interact with the human. But this is very useful for human-robot interaction, but not very useful to be used in an autonomous context. So we need to add some sensors to have mapping, localization, and detecting humans, detecting obstacles, such and so forth. And we have rectified the hardware and software architectures on this one. And this is the integration of the overall system. We have a human detection and tracking system to detect and track the position around the robot. And we use two different sensors, laser and RGBD cameras, and both detections are fused with a nearest neighbor algorithm to have a reliable result or reliable position. And we have the navigation module, which consists of map, post-processing, and path planner, because we aim to operate this robot in an unknown environment. So we need to simultaneously map and localize the robot in the environment. And due to the sensor noises, we need to do some post-processing on the map, and to work with real time with the social force model. We used another multi-level multi-level based planner, which I didn't explain because not to make it so detailed on the details. So our path planner is fed by the map and also by the path from the global plan, and it produces the control commands to the control system, and we drive the robot using the ROS serial Arduino-based control system. Okay, these are our simulation experiment. In this experiment, before we go into the real robot, we just wanted to see how the algorithm works on the simulation environment. We have defined two experiments on the simulation, and one is just to see if the robots can have a social behavior when approaching the human. The other one is, what if there is an obstacle, what can be the limits of the sociality. So on the first experiment, I also this is the social space of the human, and we see that the robot is coming, and then it plans its trajectory to have a social to ensure the social distance. And this red one or the magenta one is the classical approach or traditional approach, which just take the safety into account. Okay, this produce a safe navigation, but not a social navigation. All right, because at the end it doesn't crash or harm the people, but from the social context, it is not accepted as a social. And here we see that there are some repulsive forces from the obstacle, so it adjusts its motions again in a social manner. So we have verified our algorithm with the simulation, and this was the static world experiments, and we also tested our algorithm in a dynamic human environment. So here 5 people is in a passing in corridor scenario, and this one actually the blue one is the human force, the green one is the attractive force to the goal, and it's predicting, you know, the conflict point, and then apply a force from that point. And we successfully move to the goal point. And this is the software architecture. This is the social force model, and it's subscribing the people position, robot position, and static position, and then produces control commands to drive the robot, and also giving some visualization to the system. And these are the evaluation metrics that we have used from the literature. It's actually, this is SII, social index, is defined to measure if the physical and psychological safety is satisfied or not. And the second criteria is the relative motion index, is trying to analyze if the robot proactively plan its trajectory while avoiding the dynamic humans. Okay, then I will show my real-world experimental results. Then I will finish my presentation. Here we have defined 4 different scenarios. One is no static object, nothing on the environment, to see just our robot controller is working or not. And we have added a static obstacle into the environment, and then dynamic humans on the environment. And this is the experimental result of the free navigation case. We have started from this position and incrementally assigned different goal points, and we have seen that the robot successfully arrived at the positions, and these are the map of the environment, and this is the grid cell environment too. Because the problem is in this experiment is this problem is that there are, if the resolution of the map is very high, you mean there are a lot of points. So for each point, you need to apply a repulsive force. So it cannot be real time if you want to make so much calculations. So that we have defining the lines, and then we have detecting the lines on the map. First, actually, we are filtering out the noises on the map, and then detect the lines, and then put a grid cells to reduce the computational cost. Okay, these are the static experiment tests. I will show you the video. And this is a joint work with the Yıldız Technical University. And here we have conducted the experiment with the lecturer Furkan Çakmak from the computer engineering department of the Yıldız Technical University. As you see, this was an unknown environment, and the robots are exploring the area while it's localizing itself on the environment. And this is the goal point. Now a different goal point is given. Now the robot is trying to reach this goal point, and it's continue on. There is no social navigation case here, just controlling the robot controller. And let me move to the statical obstacle case. Yeah, so this is the static, just to see if the algorithm can avoid from static obstacles. As you see, we are using the grid cell approach to calculate the repulsive forces from the static obstacles, and it detects the table, and we are going to see a force will be applied, but it's very small, I think. And these are the real-time representations of the environment from the robot perspective, how the robot perceive the environment, right?
When you say the force,
yes,
because of that static object, that means the existence of the object, somewhat algorithm creates a force to move away, right? That is the force you define. Is that
yes.
so?
Yes, once we have detected the position of the obstacle, we just calculate the Euclidean distance towards the robot.
And you define a force so that
yes,
the robot moves away from the target, right?
Yeah, we are.
When you say human forces as well, existence of the human being creates a force for your robot.
Exactly.
The humans are not pushing your robot.
No. It's
okay.
Artificial forces,
okay.
Just to drive, just to behave, just to let robot to
forces.
behave.
Okay.
Yes. Yeah. Actually, you see, there are no forces here, but we can visualize the forces.
So the presence of the obstacle, you define a force so that you create your road to reach the target.
Yes. This approach is very good candidate to be used in the human environment because it's online. It's not so computationally expensive, and it can be flexible to define different to add different social cues or the social interactions. You can be extend. For example, if you want to, you can apply a force from a group of people. For example, you can apply a force from the center of the group to push the robot, not to interfere to the human groups, for example. Or another, for example, you may want the robot to pass from the right side of the human, so you can apply.
You put that in the algorithm so that, like, two people talking, we don't want the robot pass in front of, intersect our chatting, maybe in the corridor.
Yeah. The good thing is you can think as geometrically. So once you can imagine what you want, you can make it geometrically and then apply it as a force mechanism, for example.
Maybe the advanced level for this would be like when I'm taking a picture of people, and when you walk, you see us and detect that there's this action going. So you say, "Oh, sorry," and you pass around us, right? Because you don't intersect with the photo shooting. The robots, maybe the road will be safe for him, and he will just walk through that scene. But for the advanced level, this type of algorithms maybe will be plugged into the codes, right?
Exactly. Do you see a human duck face on the robot tablet here? Actually, we have done some experiment with it, but not used on the social navigation context. For example, sometimes as human beings, we can give some signals, right? For example, we can close our eyes. Okay, I saw you. So we are aware that we are not going to crash each other, right? We use some, so for maybe it can be also enlarged with this kind of things to have more improvement human-robot interactions, because there is no, actually this is a non-verbal interaction. Just try to understand the intention or prediction of the human motion, and then robot acts accordingly. But when there is a much rich interactions, it can be more valuable.
Okay.
Okay, I'm almost.
Are you done? Okay.
Here, this is the robot camera, and this is the environment. In unknown environment, the robot is going to start here, and I give the goal point, and the human is coming along the goal.
A moving object.
Yeah. Here, for example, you see that the RGB detector is detected the human, and also we have a laser detector. We are combining. Here you see this is the laser detector result, and this is the RGB. There is some mismatch. So here we rely more on the RGBD weighted more reliable.
RGB data is more reliable, you're saying?
Yeah. And then after some minutes, it starts tracking. Yeah, you see.
Okay, and
tracking and then it actually applies the force to the nearest point from this point actually.
And goes around the moving object, right?
Yeah. It's proactively. I have, slowed down the picture, the video.
Yeah.
And we also try with two human scenarios. Here, yeah. It applied scenario, applied the force, human force.
And also reaction time is important also. If you have a running human, the reaction time is shorter
Yeah.
for your robot, right?
And the other thing is the field of view. For example, when the robot turn left, the camera view is also turning. So you lost the
out of view, right?
Yeah, for human detection. So in that case, we rely on the laser detector. For example, as you see, when the robot turn left, since we have only used one camera, so it is a better idea to use multiple cameras to cover the maybe 360 of the field of view.
Yes. It's really interesting and inspiring work.
Yeah, this is the Yıldız Technical University Computer Engineering ground floor.
Ground floor, yeah.
Yeah, we study very closely with the probabilistic robotics group from the Yıldız Technical University with the Sırma Hoca. So I really thank for his group to have this study together.
Okay.
Okay, these are the some results for the evaluation, and I will finish with the advantages and the limitations of the study. Since we aim to work with the unknown environments, this navigational model is suitable to work with the SLAM because it has a huge amount of computation to calculate, and it is computation efficient for real time. With the dynamic K point selection, the local minima drawback is removed, and it's flexible and extendable theoretical background easily. Robot perception may be a heavy limitation because when more people around the robot, you need to be tracked many more people. So in that case, you need the robot perception may be a limitation, and also there are some parameters to be estimated for the force parameters, the magnitudes or the range parameters. So this needs to be calibrated. We have calibrated them in the simulation environment, but it's slightly changing. We have used on the real world environment, and there is also an inherent constraints to directly apply to the robots. So at least we need a robot controller to implement the idea on the real robots. And I would like to thank you for your attention, for listening. And if you want to have more discussions or questions.
Thank you very much, Hasan. And we have some questions, but before reading the questions, we have a 10-second inquiry. Anketimiz var. Bu arada ekrandan onu cevaplayabilirsiniz. So I'm reading the first question from Emine. For example, if the person is running towards the robot, how many seconds does it take for the robot to change its path? Did you also have the reaction time for the robot?
Yeah, actually, in that time, it is better not to take action. Just stop because you cannot estimate in such a close time. Maybe we can detect by laser data. Laser data is very quick. We get 30 laser scan in a second. If we have a very good laser detector, we can detect its motion, his or her motion very quickly, and its reactive time.
But I guess you didn't test for running people, right?
No, just walking, and it's on normal.
For the next level, you will go faster moving objects, maybe.
Yeah, maybe.
Hocam, Sırma hocam, buyurun.
Maybe I can make some contribution here. As you said, and Hasan said also, it depends on the reaction time of the detector, laser or camera, and also the motors and the robots construction. We have later on, Hasan doesn't know about that, but we have a Festo robot which is quite fast. We have tested on that, and when you are running in a normal speed, like I think 5 meters per second speed, it can react in a second, and even if you are very close, it can avoid you. But as Hasan said, maybe it is better to stop at that situation. But we are able to avoid, maybe in another time. We will be able to show you the that work. It is really depend on the robot as well. The robots we have used in Hasan's study is not very fast reacting robots, so we didn't take the risk for running people.
Okay.
Yeah, even we have deactivated the
Exactly.
the existing hardware, and we put our own controllers to drive the robots.
It was hardly carrying itself, so we just didn't take the risk. But normally these algorithms are tested in a better robot, and it can react to running people very quickly. I mean, we don't prefer, but if the robot has to avoid, it can do it.
Okay. There's this another question from Ryan Sultan. Could the robot avoid human without having a camera? And you had your camera, that is the RGB detector, is that? And
yes.
There is this another laser, right?
Laser detector, yes.
Okay.
It's based on the lag detectors. Actually, it's because the level of the sensor mounted to the robot is important to detect to perceive the environment, and the laser can just send the scans just on one surface. There is no much field of view.
Okay.
So maybe lag patterns or other methods can be developed, but there are many false positives on the environment, like the table legs or other objects similar to have a lag patterns.
So sound detector is not a good solution for that. Sound detector. Brian is asking for sound detector.
Sound detector, we can get distance, just the distance information, but in laser we have again distance, but since we have covering a much large area, we can detect the patterns, but for the sound sensor, it may be hard to detect.
I can also give some contribution there as well. Sound signal is very scattery, so it can give wrong information to us, and we have also tried them very early times in our work. No, actually, they are not reliable as laser, and the distances you can measure with sound detectors are not really very well, and the response time, light speed is always better than sound, so and the scattering is too much on sound detectors, so we better combine as many as sensors together. Camera is important to make sure that the object you are seeing is a human or whatever it is, to recognize the object. But laser is also very critical since they are much more sensitive compared to the others.
And I want to say the very last words. I mean, like when you say annoying, because you don't in your studies you don't want to annoy people, but as you say that, I don't want to robots move towards me, right? This is the physical annoyance. But when you say annoying people with robots, I mean, my first thing into my memory is like the appearance of the robot, like the Boston Robotics, right? The first version, I guess, it was really creepy and scary. Maybe they were using for the military purpose. That was fine, I guess. But it's not the kind of robot that I want to see in my real life. So So also the design of the robot is important, I guess, and that is totally different field of the area, right? Sırma hocam.
Exactly. Actually, we are not talking about the annoyance you meant in this study.
Yeah.
Disturbance is the right word, I suppose. When you get too close to people, even as a human, when another person comes very close to you, you get disturbed. So
Yes.
Instead of that, we try to keep a safe and social distance from the people. And on the appearance, we have to work a little more. Of course, we are using some nice screens and tablets and put some smiley faces on them.
Yeah, like cuteness of the robot.
For children, very interesting. Hasan knows about that even more maybe. For children, they react very well, but for adults, even that is not very interesting, or sometimes it gets scary, disturbing, annoying. So they don't like, adults don't like robots very easily. So we have to work on, it's not our job actually.
Yeah, that's the design part.
Yeah, it is designer's job. I think
to focus on the detection part, yeah. And
as
the
you may
performance
know,
of the robots.
Yeah, they are getting more and more like human, but that's another question. You may not like the machine to look like you very much. There is a very fine line there.
There's a critical line. I mean, that is cuteness, being cute and creepy. There is a
Ankali, that is the Ankali Valley. There is a valley. If you are very similar to humans, you drop the valley and become scary.
Yeah, if you turn into Terminator type of robot, I don't want. Okay, thank you very much. I guess we don't have any more comments and questions. I would like to thank all the speakers and the collaborators of the speakers from the Hasan Kıvrak and Hooman Hedayati and Merve ARITÜRK'e and Sırma Hocam, of course, Hatice Hocam and Daniel Zafir from Colorado.
Hocam,
I would like to, efendim.
Anketi başlatalım mı?
Yes, arada söylemiştim ama sen kaçırdın onu herhalde anketi göndermen için. And if we have a 3-question 10 seconds inquiry, if you are quick, Hasan, Ömer.
Start.
Yes, we have a 3-question inquiry. If you can answer the questions.
It appears on your screen, just click the options.
And I would like to thank also all our speakers and the attendees. I would like to thank you all. And next week we will be talking about machine learning, exactly the same time at 5 o'clock next week. I will see you. We will see you on next week. Thank you, Hooman, Merve, and Hasan again.
Yeah, we are also very thankful, and thank you for inviting me.
Okay. I would like to also thank everybody. I'm not seeing Hasan for a long while now.
Yeah.
So
it's nice to see you, Sırma Hocam.
It was nice to see you.
Okay, teşekkürler, everyone. Good evening, and see you next week.